Okay, so they got really good at interpolating. The final thing is you need good base points. You need a lot of base points from which you're able to do your interpolating. So you can find out various values of sine, special ones by Euclidean means, by using squares, triangles, pentagons. And you probably know the ones for squares and equilateral triangles. You've done that in trig, right? Like 30 degrees, 45 degrees, 60 degrees. Do people vaguely remember that? Yeah. And you can do the same thing with pentagons as well, so that's why the square root of 5 sort of turns up there. Okay, then the other thing you've got is you've got trig formulas. So you can figure out the sine of a complement of angle, right? Remember, this is cosine, just by using the fact that cosine squared plus sine squared is 1. You've got half angle formula, right? You can do sine of half an angle, right, by 1 minus cosine of theta divided by 2. You've probably more seen it as sort of the other way, where this is squared, but this is solving for sine theta on 2. And the other thing you've got is your addition and subtraction formulas for sine. So you've all seen these formulas in one form or another. And so with those, you can then find some other ones pretty easily. So you probably haven't seen these, but ever seen these values before, but you can actually figure them out super accurately. So how far can you go? So what's the lowest whole integer sine value you can figure for? Well, if you look at the values, you can kind of see everything is basically divisible by 3. So sine of 3 degrees is kind of like the lowest sine value you can find of a whole degree, right? And if you think about it, you can get sine of 3 degrees either from, you do a difference of 75 and 72, or you look at the difference between 18 and 15. So sine of 3 degrees is the best you can do. And if you go ahead and use the subtraction formula, you get this kind of little complicated formula there. It looks terrible, but it's just a square root. It's just nested square roots. So if you've got enough patience, you can figure what that is to as many places as you want. You just keep on doing the algorithm and you can create it, right? So our last hero is Jamshid al-Kashi, so early 15th century. He's kind of the last of the great Islamic mathematicians. So he was working in Samarkand. So by this time, the Mongols had been, and his patron was Tamerlane, who you might have heard of. He also worked for his son, Uleg Beg. So this is a Khanate of some kind. And he figured out sine 3 degrees to 1, 2, 3, 4, 5, 6, 7, 8 sexagesimal places using r equals 60. Now, he was working in Nasr al-Din's work. Remember, we talked to me before. He was the guy who came up with the sine law. He wrote this great book called The Transversal Figure. So it was kind of like one of the classic trig books, and he was just updating it. He's actually more famous for computing pi to 9 sexagesimal places, which was the most accurate most accurate value of pi until I don't know, the 1700s or something like that. So this is the most accurate value of pi in the period that we're looking at. Okay. So he figured out sine 3 degrees to super accurate lengths, right? And he has to, right? Because he's going to use this as kind of like a basis for his tables. And that's the lowest value that he wants to do. He also discovered the triple angle formula. So in our form, it's sine 3 theta equals 3 sine theta minus 4 sine cube theta. Has anyone seen this before? It's something you kind of might have seen. Who's doing Viet in the Renaissance? So he's a French method. He's often credited with finding this formula, but of course, our Kashi found it before him. Now, in his form, because he's using r equals 60, right, he's got to multiply things by 60. So you can multiply everything by 60. You can then divide by 60. But since you've got a sine cubed here, you've got to multiply. So he divided by 60 cubed. This. That's his form. Okay. So he knew this and he knew this. So he's going to let theta equal 1 degree. So he knows sine of 3 degrees. And so if this was sine of 3 degrees, this would be an actual equality, but it's an approximation, right? So now he's got a formula for sine of 1 degree, and he's going to approximate sine of 1 degree. So he takes this sine of 1 degree and he solves for it. Okay? And so here we've got sine cubed of 1 degree over that. And so he wants to turn that into a unit, so he multiplies top and bottom by 45(0). Whatever 45 times 60 is. Okay, and now you're going to use this to, and the thing that he noticed was, let's have a look at this expression. Sine cubed of 1 degree, what's that going to be approximately? If sine of 1 degree is approximately 1, what's sine cubed of 1 degree then? It's going to be approximately 1. This is 47.6. So this dominates this. Okay? So we know approximately what sine of 1 degree is, right? It's sine of 1 degree is chord of 2 degrees divided by 2. So it's approximately 1/250. So sine of 1 degree is 1/2 something. And this A here, it could be 50, it could be 49, depends how things round. Okay, so, well, 1/2 is 4630 divided by 45(0). So if sine of 1 degree is 1, 2, A, B, C, D. We're trying to find what these A, B, C, D is, right? So we get rid of the 1, 2, and we get 0, 0, A equals 1, 2 cubed plus 36. Yeah, because we've subtracted this from that. Okay. Well, what could A be? If A equals 0, for example, this side here would be 0.4939. If A was 60, the most it could possibly, that's over what it could be, overestimated. This would be 0.4943. So the conclusion is A equals 49. You go from the low to the high, and you see that this digit does not change. So we've shown that A is 49. So what he's got here, because this kind of thing, so he's found a way to just figure out the digits one by one. So if he can figure out sine of 3 degrees is to as many places as he like, he can use this to figure out what sine of 1 degree is to as many places as he likes. Okay, so let's work on the next one. Sine of 1 degree is 1249 BCD, or 1249. Again, we figure out what it is. That's a fraction. And so now we solve for 00 BCD. Okay, and so we subtract that from the previous thing, and so we get this. And again, the value of B does not influence what number you get here. And so we can read out that it's 43. And he just goes on ahead, on and on again, cranking the machine to get sine of 1 degree. Okay, so what do you think of Al-Kashi? So people at the time, they called him Al-Hisab, which means the calculator or the reckoner. And he did the same thing with pi, so he was very, very good at computation. He was the guy who also came up with decimal notation very early on. So he was just a great person at calculations. So he really, really, really understood. He was also kind of the heir to that line of Al-Karaji and Al-Samawal that we learned before. So he really, really understood sort of algebra, like the structure of polynomials and numbers. And he used that in his computations. And so based on this, so he died in around 1426. If you remember in the first slide that I showed you, there was the tables that were every 1 minute. They were based off his work. So now he had a way of trisecting angles that made his table, that allowed them then to work to such incredible accuracy. So that's that. Okay, so that's true. Any kind of questions about that? I think that is that's a pretty amazing rate thing. Nowadays, do people know about contractions? So that's a way, like if you've got a formula, it's like when you're iterating something, you want to find the fixed point of something. So you want to solve x equals f of x. And so, for example, say you want to solve x equals cosine x. Okay, so we know that this is something that is kind of hard to do algebraically, right? Because, well, how do we solve things algebraically? We like to imply inverses, right? But if you do inverse of cos, you then get x equals cos inverse of x. And then to undo that, you've got to do cos, so you're like in a loop. So you can't solve it by algebra. But this is very easy, actually, to come up with a highly accurate answer. All you've got to do is get out your calculators and start pressing the cos button. And if you press the cos button for like 100 times or whatever, you'll find the answer there, the solution to this to as many decimal places as your calculator can do. And the hot thing that works is you've got a contraction. So that means that it's like the input becomes the output becomes the input, and you just do that over and over again. And what's happening is it's taking some interval, and each time you apply cosine, we know that the derivative is less than 1. So it makes the interval smaller. So each time you apply cosine, you're making the interval of possible output smaller and smaller and smaller and smaller. So eventually, it reaches the limit of computation and you get just a single answer. And so these things is a really good way to solve equations numerically. But anyway, that's that. Usually you don't hear about that as an undergraduate. You've got to go to more specialized graduate classes to learn about that sort of stuff. Okay, that's that chapter. How's everyone feeling?